Today we're going to finish up our discussion about factoring by looking back at our special cases. A little while ago, when we were foiling, we talked a little bit about foiling special cases. And I mentioned at that point in time that you might not really care when you're foiling because you can just foil. Why do you need to recognize that it's a special case? And my comment was that somewhere down the road, it would be helpful to know that it was one of those two special cases when you have to work backwards. And well, down the road has come. That day has come. We are here today. So this is our last discussion in this kind of half of the unit. And we're going to finish up factoring today. And then we will just be mixing up factoring for a little bit. So first off, they look perfectly normal. Quadratic trinomials here. Let's start. But look, if we were here, we have to look at the 25. Is it 1 and 25? Is it 5 and 5? I mean, you get down here, you look, and you could have possibilities out front. Is it 4 and 1? Is it 2 and 2? On the back, is it 1 and 9, 3 and 3? And then, man, look down here. What a mess, right? So what we're hoping to do is, can we recognize that potentially this is a special case, and if it is, it narrows down the possibilities and gets you to the answer immediately. So let's talk about that. The first special case is going to be called a perfect square trinomial. So if you'll notice, it's a trinomial, 3 terms, and perfect squares. I want you to look at the A and realize it's the invisible 1, and 1 is a perfect square. I want you to look at the 25 and realize that it's a perfect square. So right up here, we're looking at 1x squared. And right here, we're looking at 5 squared. If you take the 1x times the 5, that gives you 5x. And notice that the middle is doubled. That is what a perfect square trinomial gives you. It's going to give you a perfect square on the front, a perfect square on the back. If you take the square root of the front, the square root of the back, and multiply them, double it. If that is that case, then you have what I call the identical twins. So we're going to not look at the 1 and the 25. We're going to realize that this is going to be an x plus 5 and an x plus 5. So again, remember I talked about that doubling in there. You're going to notice that there's a 5x on the outer and there's a 5x on the inner. And so there's this double 5x's, which is coming in the center. So the factorization of this quadratic trinomial is x plus 5 quantity squared. You can write it either way. It is legitimate, but normally if it's the identical twins, the best way to write it is quantity squared. So one of them. This means take x plus 5 times itself. It's a shorthand way of writing it. Let's take a look at this next one and see if it's a perfect square trinomial. So on the front, again, I'm noticing that we have a 1, which is a perfect square. We have a 16, which is a perfect square. So it's a possibility. The square root of 1x squared is 1x. And the square root of 16 is 4. 1x times 4 is 4x. Double it. I do notice an 8x in here, but see that minus? That means that both of the identical twins have to have the minus in there. So I didn't look at the 1 and the 16, and I didn't look at the 2 and the 8 because of this being a perfect square trinomial. I went right to this answer of the identical twins. X minus 4 times x minus 4, which is x minus 4 quantity squared. And again, you can see there's the square, x times x. There's the square, negative 4 times negative 4, giving you 16. And the doubling is that negative 4x and the negative 4x. There's 2 of them in the center. And let's take a look here. Ooh, perfect square on the front. See the 4x squared? Perfect square on the back, 9. Square root of 4x squared would be 2x. Square root of 4 being 2. Square root of x squared being x. So you see 2x. Square root of 9 is 3. 2x times 3 is 6x, and it's doubled in the center. This is the identical twins case. We're going to put the 2x on the front, the 3 on the back, and quantity square it. I didn't look at the combination of 4 and 1 on the front. I didn't look at the combination of 9 and 1 on the back, because I recognize this to be the setup for the identical twins, the perfect square trinomial. Two perfect squares in a trinomial. Now look at this one. This is where it becomes really helpful to notice that that's a perfect square, 4x squared. Notice that that's a squared. 81 is 9 squared. So if you take the 4x and the 9 and you multiply them together, that would be 36x. And 36x doubled does give you a 72x. And that minus means the identical twins both have to have a minus in there. And man, was that helpful, because 16 is 1 and 6 and 2 and 8 and 4 and 4 and 1 and 81 and 9 and 9. It's divisible by 3. I mean, 3 times 27. There's all kinds of combinations, but because we recognized it as a perfect square trinomial, we were able to factor it really quickly. So everything I just said, we're going to look at 4 examples again. Here are your perfect squares again. I gave those to you a while back. But here they are, so you can just sort of recognize them. You want to be able to recognize those perfect squares, and if you can recognize them, I'm pretty sure you're all going to be up to probably about 144. Just get up to the 400, being able to see the 13 squared, 14 squared, 15 squared, and I'm sorry, and then the 20 squared. Up, if you can get up to 15, or it'll be very beneficial. Okay, so here's basically what I just said. Perfect square trinomials can be factored like any other trinomial. You can do it by that sort of almost trial and error process. But if you can identify them, you can get directly to the answer. So what you look for is to see if the A and the C, so the number in front and the C, are perfect squares. So here it would be a 1 and a 16. So that's where you want to look. If it had been a 1 up here and a 12 back here, forget it. There's no way of doing this. The next thing is, once you notice that, you take the square root of what's in front. So 1x squared, the square root would be the 1x. The square root of 16 is 4. So I'm looking at the 1x and the 4, and I multiply it, 4x, and double it. And if that b term is twice that product, then you do have a perfect square trinomial, and your answer is going to be the identical twins, 1x on the front, and in this case, positive 4 on the back, quantity squared. X plus 4 times x plus 4. So let's check out this one. Square root of x squared would be your 1x. Square root of 49 would be your 7. If I take 7 times 1x, that's 7x. Double it, it's 14x. This is a perfect square trinomial, but this time the two linear binomials that I write as my answer are going to have a minus in there, and they're the identical twins. So I'm writing it as x minus 7 quantity squared. This is the same thing as x minus 7 times x minus 7, but this is the better way to write it. Now be careful here. I mean, I see the perfect squares here, but always remember to look for your BFF. Is there a greatest common factor, a GCF? So notice 4 divided by 4 divided by 4. So I can pull that 4 as a GCF out in front. That would leave an x squared, a negative 6x, and a positive 9. Now notice I'm still looking at those perfect squares. I've got a 1x squared out here and a 3 squared there. 1x times 3 is 3x, double it is 6x. So this 4 is going to ride along as part of your answer just for the ride, and then I'm going to have that x minus 3 quantity squared. Now remember that all of these can be checked by foiling back. So you could come up here and take x plus 4 times x plus 4 and do the FOIL multiplication, first, outer, inner, last, and you should get back to this. You can always check your factoring. Now if you've pulled out a GCF, you would FOIL first and pretend the 4 is not there, and then distribute the 4 back in to make sure you get back to your original answer. Okay, first of all, is there a greatest common factor? It started to look like it, but the 9 tells me no. But this is a perfect square. It's 5x squared, and this is a perfect square, which is 3. If I take the 5x times the 3, 15x, and double it, sure enough, I get the center. So the 5x is the first term in the answer. The positive 3 is the second term, and it's quantity squared. And that is how we do a perfect square trinomial. So what I would recommend right now is to stop the video, to pause it, and see if you can factor these four. But let me give you a clue first. They are not all perfect square trinomials, and one of them might be especially tricky. Be careful, have your eyes open. Pause the video, give it a go, come back when you're ready to check them. Okay, let's see how you did. So if I was getting ready to factor this one, the first thing I notice is this is 1x squared on the front, perfect square. 36 is a perfect square. 1x times 6 is 6x. Double it gives me a 12x, and there's a minus here. So I'm going to have the x minus 6 times x minus 6, or x minus 6 quantity squared. All right, here's the tricky one. Here was the mean one, for lack of a better word. But if you'll notice, you're going to think this is a perfect square trinomial, but please look out at the C and notice his sign. Whenever you multiply or square something, so if you took 5 times 5, you'd get 25. If you took negative 5 times negative 5, it would be a positive 25, not a negative 25. This one, you would have to trial and error. I'm going to be honest, there is no factorization for this one, and that's called prime. Now, let's put it up front right now. On any assessment that I were to give you, I will never ask you to factor something that cannot be factored on a quiz or test or something like that. But you do have to realize that most of the quadratic trinomials in life are not factorable. So as we go on to the second half of this unit and we're talking about solving, we're going to have to, talk about other methods. But right now, just realize from a factoring standpoint that this one doesn't have two pairs of linear binomials that will multiply. And it's definitely not a perfect square trinomial, because to be one, it always has to be plus on the C, because identical twins, if they're both negative, it'll be a positive. And if they're both positive, it'll multiply to a positive. So this guy was prime or not factorable. Let's check the next one. Perfect square on the front of 1x squared, and perfect square 4 squared. 1x times 4 would be 4x, double it would be 8x, and it's not a perfect square trinomial. Now, is this one factorable by another combination? Well, to get 16, it doesn't just have to be 4 and 4. You could have 8 and 2. You could have 1 and 16. And notice that 8 and 2, since remember we've only got a 1 out here, so this is the easier case. That 2 times 8 will multiply by 16, and that 2 plus 8 will add to 10. So that would be my factorization. And the last one here, before I go anywhere, I'm going to notice that there is a greatest common factor. So the first thing I'm going to do is factor out that 9, and boy, does that make this a lot more pleasant to work with. So 9 times x squared would give me the 9x squared. 9 times negative 4x would give me the negative 30x. And 9 times positive 4 would give me the positive 36. The 9's going to come along for the ride. And now I'm looking at this guy. And notice he's a perfect square. And she's a perfect square. So this is 1x squared. And this is 2 squared. 1x times 2 is 2x. Double it. This is a perfect square trinomial. And we have a case for the identical twins. Again, it's minus because he's minus. Okay. So I want to just remind you, as we go into this section, you'll find a lot more of GCFs. So when I'm looking at this, man, I do not want to start worrying about all the combinations on the end when I know there is a GCF. So there is a greatest common factor here. So I'm going to wait a second and see if you can figure out what the greatest common factor is. Did you notice they're all even? So we could at least factor out a 2. So why don't we start there? Take out a 2, take out a 2, factor out a 2, and you'd be looking at this. It still looks kind of nasty until you now realize that that's a perfect square, 5x squared. And the end is a perfect square, 6 squared. 5x, 6. 5x times 6 is 30x, and double it. This is a perfect square trinomial because you've got that 30x on the outer, and it's going to be a 30x on the inner to give you the 60x. So this is going to be identical twins. They'll both be positive. 5x on the front, 6 on the back, and the 2 comes along for a ride. Now, if you were going to check this, you would FOIL the 5x plus 6 times itself, and you would get 25x squared plus 30x plus 30x plus 36, and the two 30x's would come together to be 60x. And then you would 2 times 25x squared gives you the 50x squared, 2 times 60x gives you the 120x, and 2 times 36 gives you the 72. I'll tell you, the one really cool thing about factoring is you can always check your answer to see if you get back where you started. You know if you got 100. Okay, so why don't you pause the video and see if you can factor these two completely. And don't forget, I'm going to give you a hint. GCF is your BFF. Give it a pause and come back in a second. We'll see how you did. So the first one, was there a GCF? The answer is yes, it is 3. Now remember to find divisibility by 3. If you took the 8 plus 4, you get the number 12. That's divisible by 3. The 1 plus the 2 plus the 0 is 3. 3 is divisible by 3. And 7 plus 5 is 12. And that's divisible by 3. So all 3 of these numbers is divisible by 3. When you pull the 3 out, you're going to have a 16x squared left, plus a 40x, plus a 25. And now look, see the perfect square out front? See the perfect square on the back? This is 4x times itself. This is 5 times itself. 4x times 5 is 20x, and it's doubled. So this is going to be the identical twins with a 4x plus a 5. Don't forget the 3 comes along kind of for the ride. Now the next one is basically screaming at you that there's a GCF because we don't know how to factor cubes. So if there's a cube there, the only way we can factor it is there has to be a GCF. In this case, the biggest number that divides into all of these is 5, and the smallest exponent is x. So our GCF that's going to come out in front will be a 5x. 5x times x squared gives me 5x to the third. And then minus 20x plus 100. Now the question is, can this quadratic trinomial be factored further? And the answer is yes, because look at this guy. He's a perfect square, 1x squared, and this is 10 squared. 1x times 10 is 10x, and double it. This is the perfect square trinomial. It's going to be the identical twins, and this guy comes along for the ride. And that is our final answer. Now, there is a special case, another one rather. So let's take a look at him. Just to remind you, we kind of did something like this about a week or so ago. If we were to FOIL these, this is the case where we get the x squared, and the outer is a positive 3x, and the inner is a negative 3x, which is going to fall out. The OI is going to drop out, and the last will be negative 3. So you might remember we kind of did something like this, and we realized that anytime you have, they're not identical twins, they're twins but off by a sign, you end up losing the OI, what I call the OI, the middle term. 3x times 3y, and negative 2 times 2, and you get a positive 6y and a negative 6y, and they combine and fall out. Now, when we go backwards to factor, you're going to recognize this because if you have a binomial, only 2 terms, then you can only factor possibly out a GCF, or it has to be what is called the difference of 2 squares. So the difference means subtraction. Notice 9 is 3 squared and x squared is 1x squared. Notice down here 4 is 2 squared and 9y squared is 3y squared. It is the difference of 2 things being squared. And when you see that, it is one of our special cases, and it really is the easiest one to factor. So the first thing you're going to look for if you see a binomial is there a GCF? And then the second thing you're going to look for is it a difference of two squares? And that'll tell you if you can factor it further. So here's just a little description of that, the fact that if you've got something squared minus something squared, it'll be the twins off by a sign. All right, so here's an example. I look for a GCF. There isn't one. This is 1x squared, and this is 8 squared. There's no middle term. The middle term has fallen out, so it is the twins off by a sign. It is the x plus 8 and the x minus 8, and that outer of negative 8x and the inner of positive 8x are why that drops out. No GCF. This is 2x squared, and this is 11 squared. It's the difference of two squared, so I'm going to put the 2x in the front, the 11, and I got one of them as a minus and one as a plus. So if you have the twins off by a sign, there is no middle term. If you have identical twins, there is a middle term that is that idea of the doubling that we talked about a minute ago. Okay, so see the perfect squares? See the perfect squares? No perfect squares. Might have to look for something first. Why don't you pause the video and see how you do on these? We'll come back in a second and check them. 9x, 7, right? One of them is a subtraction, one is an adding, and that's what makes the middle term drop out. Did you see this is a perfect square of 13x squared, and this is a perfect square of 1, one with a plus, one with a minus. That's what makes the middle term drop out. Did you see 11? Ooh, a little tricky here. Well, how do I get something to the x to the fourth? It would be x squared times x squared. So the front is going to be 11x squared. One of them is going to be a minus 3, and the other one's going to be a plus 3. Now, this one, like I said before, looks like a difference of two squares, but these aren't perfect squares. So look for the GCF first. And both of these, 2 plus 1 is 3, 7 plus 5 is 12. They're both divisible by 3. And when I factor out that GCF of a 3, look, I'm left with a difference of two squares. So I'm going to put the 2x on the front and the 5 on the back, and they have to be off by a sign. And there's the complete factorization of that quadratic binomial in this case. Here's two more. I want to have you pause the video and see if you can do those. Again, it's not a difference of two squares if these aren't perfect squares, so look for a GCF. They're both divisible by 10. The minute I pulled out that 10, I got a difference of two squares. I got an x plus 2 and an x minus 2, and the 10 comes along for the ride. This one is shouting at you. With that cubic, we don't know how to factor a cubic. There has to be a GCF. And notice they both do have a t. So this time, just that t is going to come out. There's the perfect square. There's the perfect square. 3t on the front, 4 on the back, and they have to be off by a sign. If you were going to check this one, remember to do your foiling first and then distribute the t to come back and check your answer. Okay, this is our, I believe, our last page. So pause the video and see how you do on these. Difference of two squares, y minus 11, y plus 11, right? Difference of two squares, 5k and an 8. One with a plus, one with a minus. Ooh, not a difference of two squares. But wait a minute, there is a GCF. These are both divisible by 8. When I take that 8 out, whoops, let's pull this out over here. When I take that 8 out, I'm left with 9x squared minus 1. Difference of 2 squared. This is 3x squared. That's 1 squared. 1 with a minus, 1 with a plus. And if I'm not mistaken, we are done. So there are some great examples of special cases. The two of them are the difference of two squares, which we just did, and a perfect square trinomial. Let's see how you do with that. There'll be a worksheet. Give it a go, and remember, practice makes perfect. Have a great day, everyone.